Hi everyone, this is the second video of chapter 22 about rate of reactions. In the first video, we have learned about rate of reactions, method for following the course of reaction, collision theory, and also the factors affecting rate. In this second video, we will learn about calculating rate of reactions graphically, and then we will learn about what is rate equation and what is the rate constant and how to calculate it, how to calculate the rate constant. Okay, so this is the focus on this second video. Okay, so let's continue with our focus today. First is about calculating the rate of reactions graphically. Okay, this table shows about the concentrations of reactant, which is the cyclopropene, and the product, which is propene, at 5-minute intervals with temperature 500 degrees Celsius. We can make the graph between the concentrations of cyclopropene with time, and the graph will be like this. Once again, cyclopropene is the reactant, so that's why the concentration will be decreases with time. Okay, once again, the title for this is calculate the rate of reactions graphically. Calculate the rate of reactions graphically. At the beginning, actually, I already told you that when we want to find out, for example, the rate of reactions at a particular of time, we just need to make the lines, connected the time until it reaches the curve. Okay, until it reaches the curve. So this is the point, and then later on, please find to another point closest to the this point. Okay, but still in the curve, and then you should make the line, to connect these 3 points. Okay, you can see that we can find later on, we can find the tangent, through the difference in concentrations of the cyclopropane, which is 1.4 minus 0. Okay, this is delta concentrations or delta y. Okay, and then over the time here. Okay, this is around 35. Yeah, around 35 minus 0. So you can use your calculator to find out what the rate of reactions in at 10 minutes. Okay, so this is how we measure the rate of reactions graphically. Okay, I already told you in the first video that rate of reaction is not constant. It will change, as the reactions proceed. So we can calculate some rate of reactions. So for example, if we want to find the rate of reactions when the concentration is 1.5 mole per dm cube. So once again, you need to draw the tangent. Okay, this is the tangent. Okay, and then you should find the delta y minus delta x. Okay, in this case it's 1.5 minus 0 over, this is 25 minus 0. Okay, so 25. But since the unit of rate of reaction is mole pm to the power of negative 3 second to the power of negative 1, so since this is in minutes, we should multiply the time by 60 to get the unit in second. Okay, and then if you want to find the rate of reaction, for example at the concentration 1, okay, you can try to make to find a point. Okay, you can make the line from the concentration to the curve. Okay, after you get the point, okay, this is the point. Okay, you can find out two other points closest to this point, and then you can make the second line, yeah, to find out, yeah, the tangent. Okay, for this is 1.4 minus 0 over 35 times 60. Okay, so this is the rate of reactions when when the concentration is 1 mole per dm cube. Okay, you can find out that the rate of reaction decreases as the reactions proceed. Okay, and then if you want to find, for example, at the concentration 0.5, for example, 0.5 here. Okay, once again, do the same method. Okay, this is uh, the tangent. Yeah, this is the tangent. Okay, so the rate of reaction will be decreases as well. Okay, so for the reactants, the rate of reactions will be decreases as the reactions proceed, since since it is used up. Okay, so that's why the rate will be decreases. Okay, but if you want to find out about the linear plot of the graph, we can find through the ratio between the rate of reactions with the concentration. So let's say if I want to make the linear plot of the graph, I will make the table here. Once again, you can see that I already find the rate of reactions when the concentration 1.5, and then 1, and then 0.5. So I will put the concentration data here, 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 and here. Then the rate of reactions that we just measured, here, here, and here. Okay. After this, after we calculate the rate graphically, I will teach you about the rate equation. Actually, the rate equation is K times the concentrations of the reactants to the power of something, to the power of order. Okay. In this example, I will use the first order reaction, which is the order of reaction is 1. Okay. So you can see the relationship that K equals to rate over concentration. So that's why you can see that this table, this third column shows about the ratio between the rate with the cyclopropane, because this is shows us about the rate constant. You can see that if we divide the rate with this concentration, that we get the same numbers, which is around 6.6 times 10 to the power of -4. This is we call as rate constant. Okay, so if you want to make the linear plot, you can make the graph between the rate of reactions with the concentration. So the slope here shows us about the rate constant. Okay, which is rate over the concentration of cyclopropane. Okay, understand? So once again, how to find the rate of reactions? You should make the graph between concentration and time. This is the first thing that you should do. Make the graph between what? Concentration and time. Later on, you should pick some concentrations or some data here, and then makes the tangent to find the rate. Okay, to find the rate. After you find the rate, you can divide the rate with the concentration to find the rate constant. Make the graph between rate and concentration. Okay, so there are two types of graph that we should understand in this chapter, which is concentration versus time and the rate of reactions versus concentration. Okay, this once again, this is how we calculate the graph, the rate of reactions graphically. This. Okay, understand? I hope so. Okay, now let's practice. Plot the data in table 22.1 for increase in propene concentration with time. Propene concentration with time. Okay, this is the table. Just now we have seen that the concentration of cyclopropane is decreases with time. But how the propene? Since the propane is product, then the propane will be increases with time. Okay. So please try to make the graph between concentration of propane with time. Please pause this video. Okay, let's continue. Okay, you have make the data, the graph between the propene concentration with time. After you get the graph, calculate the rate after 10 minutes. Yeah, when the propane concentration is 0.5 by drawing a tangent. Okay, so once again, we should calculate the rate after 10 minutes. Which is the propane concentration is 0.5 by drawing tangent. Okay, I already make the graph, yeah, using Excel here. Okay, this is the time with the concentration of propane. Okay, you can see that since propane is a product, then the graph will be differ, yeah, with the graph of cyclopropene. I will zoom this. Okay, we need to make the tangent to show to measure the rate of fractions after 10 minutes. Yeah, or when the concentration of propene 0.5. What we should do is find a point first. Okay, find a point. Okay, after 10 minutes, so here, okay, find a point. This is our point. Okay, how to make the tangent? Okay, since this is our point, we should find the two closest point. Okay, for example, I will use the green one. Okay, I think this is the closest point. Okay, next, I'd like to make the line. Okay, here like this. Okay. Okay, after we get after we already make the line, we should make the triangle. Okay, how to do this? Please remember that sorry, that the point that we are looking for, yeah, which is the pink one, yeah, should be located in the middle of the hypotenuse of the right triangle. Okay, this should be the, once again, should be in the middle of the hypotenuse. Okay, so wait a minute, I will use this. Okay. So for example, I will choose this point. Okay, here. And this. Okay. Okay, and then this. Can find this is the triangle. Okay. This is the triangle. And okay, we should find this tangent. Okay. So tangent is, once again, this over this. So what's the value of delta Y? Our delta concentration is around 0.2, right? How about the time? We need to make one another line here. You have to see time. When was this not perfect once again? Okay, like this. So I think this is around 13 and this is around 8. So 13 minus x, 13 minus 8, around 5, right? And then you should multiply by 60. Yeah, since it should be in second. So is your calculator 0.2? Okay, over 300, right? So the result is 6.68 times 10 to the power of negative 4 mole dm minus 3 second minus 1. Okay, so once again, if you start from the concentration of reactant over time, then you will get this curve. Yeah, this curve. And to find out the rate of reaction, you make this tangent, okay, until you reach the x-axis and y-axis. This is the x and y, the delta x and delta y. But if you start from the concentration of product, then the triangle would be like this, so differ. Okay, please remember how to calculate this. Okay, the next question is use the same method to calculate the rate of reactions of propene at 0 mole per dm cube. Okay, I will write here at 0 mole per dm cube, 0.3 and 0.9. Okay, let's back to our graph. Okay, at 0, how to calculate the rate of reactions at 0? So same, yeah, make the tangent, but for 0 is quite challenging since the graph will be end here, okay, but we can try to make the additional line here. Okay, so actually once again, this should be the hypotenuse. Yeah, should be in the middle of the hypotenuse of the triangle. So what we should do is make the extrapolation. Okay, like this, extrapolation. Then we make the triangle. Okay. Okay. Okay, since this is extrapolation, we can use this point. Okay, and then this is the another point. Sorry, I will change this. Yeah, since not too accurate. I will make one once again. I will choose the 2 points here, and then make the line. Okay, so I think this is the best point that we can get. Okay, and try to make the line here to get the time. So you already get the triangle here. Okay, so let's calculate the rate of fractions when 0. The rate will be delta y is 0.2 minus 0 over 1, 2, 3, 1, 2, 3, 4, 5. Okay, around 3.5 until 4, yeah? Let's say this is 3.5. 3.5 minus 0 times 60. So the result is 9.52 times 10 to the power of negative 4 mole Tm minus 3 second minus 1. Okay, next, at concentration 0.3, the same method. Okay, 0.3. Let's clear this, yeah? Okay, let's clear this at 0.3 and at 0.9, yeah? At the concentration 0.3 and 0.9. Okay, so now let's pick the point 0.3 around here, 0.9 around here, yeah? In the middle. Okay, wait a minute. Okay, let's try to find a point. Okay, this is the point, and find to another point. Then make the line. Okay. Okay, once again, this should be the middle, yeah, the middle of the hypotenuse. Okay, so typing, we can choose this as the triangle, yeah. Wait. How about this and this? Wait. Okay. Okay. And this is our tangent. Okay, so the rate of rotation would be 0.5, 0.4 minus 0.2 over, yeah, this is around 8 minus 4, so that means 4 times 60. 140, yeah. Okay, you check with calculator. 8.33 times 10 to the power of negative 4. Yeah. Okay, the last is at 0.9. Okay, do the same method. 0.9. Okay, and then find two another points. Okay, then make the triangle. I'll make the line first. Okay. Okay, and then we already get the point. Okay, let's make the triangle. Okay, I will choose this. Yeah. Okay. Okay, you can see here that the rate of reaction would be what's the value of this? 0. How do you think? It's very close to 1, yeah? So 0.95, yeah? Let's say 0.95. 0.95 minus 0.8. Okay, 0.8. Here, this is 0.8, right? This is 0.8, I mean 0.95. Over the time, 25, minus 19, yeah? I think this is 19, times 60. So we have 0.15 over 6 times 660, 360, yeah? 4.17 times 10 to the power of -4. Okay, so you can see as well that the rate of reactions of product also decreases, yeah, with time. At the beginning, it will produce a very large number in a very large number, but after the reactants has been used up, then the rate of reactions of the product also decreases. Okay, so this how we make the graph and calculate the rate of reactions graphically. Okay, from the reactant side and from the product side. Okay, if you want to calculate the concentration of cyclopropene when the concentrations of propene is 0, 0.3, 0.5, and 0.9, how to do this? Once again, calculate the concentration of cyclopropene, yeah, when the concentration of propene is 0, 0.3, 0.5, and 0.9. Okay, we need the table, yeah, we need the table data. So I will scroll this. Okay, this is the data. So at the beginning, we have cyclopropene 1.5. Okay, this is at initial 1.5. And of course, the propene has not formed yet. And the reaction is negative X, positive X. And then after the reaction, 1.5 minus X for the cyclopropene, while X in propene. Okay, when the concentrations of propene is 0, when this is 0, so X is 0, right? So the cyclopropene would be 1.5. How about if the concentration of propene is 0.3? Then the cyclopropene will be 1.2. If this one 0.5, this should be 1.5. Oh, sorry, 1.5 minus 0.5 will be 1, yeah? And then when the X is 0.9, so this would be 0.6. Okay, so this is how we answer the questions of CI. Yeah, when the question asks about what's the concentration of cyclopropene when the propene is this, this, and this. Okay, the last, plot the graph of rate of reaction against cyclopropene concentration. Note that the graph is for cyclopropene concentration, not propene, since it is the concentration of reactant that is affecting the rate, not the product. Okay, rate with concentration. I think we already have the graph. Okay, the graph will be like this, the rate with the concentration. This. I already show you how to make this graph. Okay, you can pick some concentrations and then find the rate of reactions at the particular concentration. So you have the rate of reactions data, and then you have the concentration of cyclopropene data as well. So you can plot the rate with the cyclopropene, and then you can find if this is the first order reaction, it will make the linear plot like this. Okay. So we are done with the first subtopic, which is we learn about calculate the rate graphically, the rate of reactions graphically. Okay, the second focus in this video is I want to explain about rate equation, or sometimes called as rate expression. So this is the same term. Okay, the rate equation for a chemical reaction is an equation that links the reactions rate. Okay, you can see this, yeah, if you confused about the definition. Okay, so once again, the rate equation for chemical reaction is an equation that links the reactions rate, which is R, yeah, the reactions rate, with the concentrations or pressures of the reactants. So let's say we have A plus B becomes C. The reactants are A and B, right? So once again, links the reactions rate with the concentration or pressures of the reactants, A and B in this case, and constant parameters. So R equals to K times concentration of A to the power of X. X and Y is called as order of reaction. Order of reaction, that means if we change the concentration of this substance, how it affects the rate of reaction. So it is called as order. Later on, we will learn deeper about order. Okay, so once again, rate equation is this equation. Rate equals to K times concentration of reactants to the power of its order. Okay. You can read this slide. So concentration is expressed in molarity, mole per dm cube. X and Y is reaction order, and please be careful, often not equal to the coefficient. So please don't think that order of reaction is its coefficient. It is not. Yeah, it can be same, it can be differ, but usually it will differ as the coefficient. And then once again, K is the rate constant. Okay. Don't forget, concentration symbol is a square bracket like this, yeah? So the square bracket is a symbol of concentration. The value of coefficient K may depend on the conditions such as temperature, ionic strength, surface area, etc. Okay, so the rate constant will be changed if the temperature changes. Later we will learn deeper about the rate constant and the order of reaction. So have you understand about the rate equation? So this is the rate equation. Yeah, equation that link rate of reaction with concentration of reactants. Okay, I think already clear. So I have this question. This reaction shown to be second order with respect to NO and first order with respect to H2. Give the rate equation for this reaction and its overall order. Okay, you know that once again the rate equation equals to K times concentration of reactant. Which reactants are there in this equation? Hydrogen and NO. Okay, so I will multiply K with the concentration of H2 and NO. Now we'd like to write the power of H2. Once again, the power of H2 is its order. Okay, H2 here, and the statement is first order. So it should be first order here, but usually to the power of 1. No need. No need to write the power of 1. Okay, so I will erase this. And then for NO is second order. So I will write like this. So this is the rate equation for this reaction. Rate equals to K times H2 to the power of 1 times concentration of NO to the power of 2. What's the overall order? Overall order, that means you should add the order of H2 and the order of NO, which is 3. Okay, do you understand? So please be careful that you can see that the coefficient is 2 and 2. But in the rate equation, H2 only to the power of 1, not to the power of 2. Okay, so once again, the order of reaction is not same as the coefficient of the reactants. Okay, I think you already understand about this. Okay, so let's see this table. Order with respect to reactant 1. Okay, look here. Order with respect to reactant 1. Hydrogen and iodine. First order and first order. So overall order of reaction is second. For the second equation, H2O2, first order. No other reactants. So overall order is 1. First and first. So overall order 2. First and nothing. So first order. So once again, overall order is just the sum of the power of all reactants, yeah, present in the equation. Okay, now let's practice. Please pause this video. Let's continue to discuss about the answer. Write the rate equations for each of the following reactions. Cyclopropane to propene, where rate is proportional to the concentration of cyclopropene. So rate equals to K times concentration of cyclopropane. Okay, rate equations. How about B? Hi, where rate is proportional to the square of the hydrogen iodide concentration. So please put here square. Okay, this is B. What C? That equals to K times concentration of C12 is 22O11, and the concentration of X plus, but so times concentration of X plus, like this. D proportional to the concentration of HCl2, so HCl2, and the square of concentration of K2C2O4. Okay, like this. Okay, the last, where rate is proportional to the concentration of propanol and the concentration of H plus, but the concentration of iodine has no effect. Has no effect, that means 0. Yeah, the order is 0. So rate equals to K times propanol concentration times H plus. Okay, like this. So this is how we make the rate equation according to these equations. Okay, we have learned about the rate equation, which is rate equals to K times concentration of reactants, let's say A or B, to the power of their coefficient. So to the power of their order, I mean, okay. So now we want to learn about deeper about rate constant K. So what is K? Yeah, the rate constant K is proportionality constant in the equation that expresses the relationship between the rate of the chemical reaction, okay, that expresses the relationship between the rate of chemical reaction and the concentrations of the reacting substances. Okay, so this is the K is express about the relationship between rate and concentrations of the reacting substances. The value of K is temperature dependent, so it is constant if the temperature constant, but if the temperature changes, the rate constant will be changed as well. Units of K will be vary depending on the overall order of the reactions. So let's say we have the zero order reaction. So once again, you know that rate equals to K times concentration of reactant. Let's say the reactant has the symbol A like this, yeah. So if the order of A is 0, so you can see that the rate will be equals to K times 1, right? Because everything to the power of 0 is 1. So rate equals to K. So the unit of K is similar as the rate units. This is mole dm minus 3 second minus 1. So that's why you get here like this. Yeah, you get this value. How about the first order? So rate equals to K times A to the power of 1. So K equals to rate over concentration of A. Okay. Unit of rate is mole per dm cubed second minus 1. The unit of concentration is mole per dm cubed. So this cancel out. Then the unit of rate constant at first order reaction is second minus 1 only. The second order over mole per dm cubed square. So this cancel with this and this going up. So mole to the power of negative 1 dm to the power of 3 second minus 1. Okay, the third order, so over mole per dm cube square cube mole per dm cube cube. Okay, so this cancel, this will be square and then going up mole to the power of negative 2 dm 6 second minus 1. Okay, so once again the unit of K through the unit of K we can predict the order of the reactions once again through the unit of K. So if the unit of K is second minus 1, so we can expect that this is the first order reaction. Or if mole to the power of negative 1 dm3 second minus 1, we can expect the order is second order. Okay, understand how to calculate the units of K. Okay. Okay, pause your video now. State the units of K corresponding to each of the following rate equations. Okay, the unit for A is mole minus 1 dm 3 second minus 1. For B, wait a minute. Okay. Okay, for B, this is the zero order, so rate equals to K. So K is mole dm minus 3 second minus 1. For C, the fourth order, yeah, 2, 1, 1. So mole negative 3 second minus 1 dm of 9. Okay, this is the first order, so second minus 1. Okay, all correct? I hope so, yeah? A reaction has the rate expressions, rate equals to K times concentration of A square times concentration of B. Calculate the value of K, including units, for the reactions when concentration of both A and B are blah, blah, blah. And the reactions rate is like this. Okay, the value of K. So K equals to red over concentration of A square times B. Okay, this is the red. This is the concentration. Use your calculator to calculate this. Okay, it is 4.96 times mole negative 2 dm6 minus negative 1 ya. Okay, get it ya. Okay, let's practice again the rate constant. Okay, so this is the last topic in this video. Please pause this video to answer this question. Okay, let's answer this. Give the units of K in each of the red expressions below. For A is mole negative 1, dm3 as minus 1, B second minus 1, C mole dm minus 3 second minus 1. Okay, like that. Okay, number 17. The reactions 2N2O5 becomes NO2. NO2 has a value of K, blah, 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 at a certain temperature. Deduce the red expression for this reaction. Okay, red expression. That means red equals to K times the concentration of reactant, which is only N2O5 here. What's the power of the concentrations here? Can I use 2 like this? Of course not. Yeah. Once again, because the coefficient is not the order of reaction, so I cannot put the coefficient as the order. So how we know the order of this reaction? To find out the order of this reaction, you can find through the units of K. You can see that the units of K is second minus 1. So what the order? Order of reactions when the K has unit second minus 1 is the first order. Okay, I hope you remember. Okay, I will scroll this once again. This, yeah, first order, second minus 1. Okay, so the red equation for this would be red equals to K times N2O5 to the power of 1, or no need to write anything here. So this is how we answer question number 17. Yeah. Okay, 18. A reactions involving A and B is found to be zero order with respect to A and second order with respect to B. When initial concentrations of A and B are blah blah blah, initial rate of reactions is blah blah blah. Calculate the value of rate constant for this reaction. Okay, first we should make the rate expression. Okay, rate equals to K times concentration of A order 0 times concentration of B second order. So this equals to 1. Okay, rate equals to K times concentration of B square. So if we should make if we should measure the value of rate constant, which is K, rearrange this formula. K equals to rate over concentration of B square then put the data over b, where is b? This, yeah, 2 times that of negative 3 square. So what's your result? K equals to 1.1 times 10 to the power of 2. What's the unit then? Mole per dm cube. Mole per dm cube square. Second one is 1, yeah. This is square. So this is cancel. This cancel, I mean. Okay, cancel with this. So the unit is mole to the power of negative 1 dm to the power of 3. This is in minutes, not second, yeah, in minutes. So minutes, negative 1. Okay, done. Okay, good. Okay, once again, that constant is temperature dependence. So the rate constant will be changed if the temperature changes. You know, in the Maxwell-Boltzmann distribution curve, we can see that as the temperature increases, the curve will be have the lower peak and wider or spread out. Okay, so as the temperature increases, the probability of molecules having energy more than activation energy will be increases as well. Okay, so we hope that the rate of reactions will be faster. Okay, according to Arrhenius equation, okay, actually this is not in your syllabus, but I want to explain this if you need a deeper knowledge about kinetics. Okay, for those who want to know deeper about kinetics, you can still listen to this video. But if you think that it is enough for me, yeah, you can stop this video right now. Okay, but if you want to learn, yeah, you can see that how the rate constant changes with temperature. Okay, once again, this is Arrhenius equation. Arrhenius equation shows about the rate constant equals to the frequency factor, or A, times epsilon to the power of negative EA, activation energy, over RT. R is ideal gas constant. You know that the value is 8.314, and the temperature should be in Kelvin. Okay, so once again, K, the Arrhenius, the rate constant equals to frequency factor, or pre-exponential factor, times epsilon to the power of minus EA over RT. So that's why if the collision increases or the frequency factor increases, the rate constant will be increases, then the faster the rate of reaction. If we plot through the graph, we should plot the ln K versus the 1 over T. Okay, you can see that ln K is equals to Y, and this equals to M times 1 over T is X. That the dependence variable in this graph plus C. So Y equals to mx plus C. So the slope equals to negative EA over R. Okay, so if we know the value of the slope, you can find what's the activation energy of this region. Okay. So if the K changes with the temperature change, we can find that, for example, at T1, the K will be labeled as K1. So ln K1 equals to negative EA over RT1 plus ln A. Okay, at temperature 2, ln K2 equals to negative EA over RT2 plus ln A. If we subtracting the second equation from the first, okay, so ln K1 minus ln K2, this would be negative EA over RT1 plus ln A minus this, right? So ln A minus ln A can be cancelled, okay? And this will be changed to negative EA over RT1 plus EA over RT2. Or we can rearrange EA over R 1 over T2 minus 1 over T1. Ln K1 minus ln K2, that means ln K1 over K2. So that's why we can have this formula. If the temperature changes, the value of K, the rate constant, will be changed as well. And we can find the new rate constant at the new temperature. Okay, so once again, this is we call as Arrhenius equation. So let's calculate this. Okay, let's find out the ln K1 over K2, once again, EA over R, 1 over T2 minus 1 over T1. So ln rate constant, this is K1, this is K2. So ln 3.552 times 10 to the negative 7 over equals to EA, we should find EA here, EA over 8.31 times 1 over T2, should be in Kelvin. So you add this by with 273. This is T1, this is T2. So T2 is 781 minus T1 556. Okay, let's calculate. I got EA equals to 1.87 times 10 power 5 joules per mole. Yeah, joules per negative 1. So once again, through this Arrhenius equation, we can find the K or the EA. Yeah, it depends on the equation. Okay, but the focus in A level is just if the temperature changes, if the temperature increase, the rate constant will be increases as well. Yeah, since the frequency of collisions will be increases as the particles gain more kinetic energy. Okay, I think you're already tired, but I still need to explain about this. Okay, this is calculations involving the rate constant. We can calculate the rate constant from initial concentrations and initial rate. So there are 3 ways to calculate the rate constant value. Okay, first is by using the initial concentration and rate. Second is from the graph rate versus concentration. And then the third from the half-life. Okay, so there are 3 ways to calculate the rate constant. Okay, let's see this one by one. Calculating the K from initial concentrations and initial rate. So if we already know the value of rate and the value of concentrations, we can easy to find the value of K by rate over the concentration of the reactants. Yeah. So if you already know the value, just fill with the value and the value of K will be produced here. Okay, this is the first method by initial reactions and initial rate of reaction data. Okay, the second is from graph. Okay, this is the graph of absorbance versus time. This is same like concentrations versus time. Okay, we cannot find the K through this type of graph, but through this graph we can find the rate, right? Yeah, at a particular time we can get some rate of reactions value, and then after we get the rate of reactions value, we can calculate the rate constant by divide the rate of reactions with the concentration. Okay, so we can find the graph like this, the linear plot of graph. Okay, so we can find that this is proportional with the rate constant. So the slope is the rate constant of K. So this is how we measure the rate constant value through graph. Okay, so please remember the graph is between the rate constant, between the rate with the concentration. Okay, the third is from the half-life. In A level, you just need to learn the half-life of the first order reactions. Once again, the first order reactions. So K will be equals as 0.693 over T half. Just use this formula. In the third video, I will explain about how to derive this formula. Okay, but for now, please accept this. K equals to 0.693 over T half. So for example, the half-life value already known, then you just need to use this formula. Okay, K equals to this over the half-life value. Okay, so those are three methods of how we measure the rate constant. So okay, this is the last practice question. We have some experimental data here. This is the reactions between hydrogen peroxide, iodide, and H plus with initial rate of reaction. Okay, use the data from experiments 2 and 3 to calculate the rate constant for the following reaction. If the rate reaction is equals to K times H2O2 times I minus. Okay, please pause this video and try to answer it. Okay, let's discuss the answers together. Okay, we should use experiment 2 and 3 to calculate the rate constant for the following reaction. Okay, this is experiment 2. We can find that the rate of reaction is this. Okay, since the rate equation for this reaction is H2O2 times I minus, that means the concentration of H plus is not affect the rate of reaction, so we can ignore the concentration of H plus. Okay, so we can ignore this. We just use this and this value. Okay, according to the explanations before that, we can find the rate constant value through the initial rate and concentrations of reactants. Okay, so K equals to rate over H2O2 times I minus 5.3 times 10 to the power of -6 over 0.03 times 0.01. Is 0.0177. The unit would be mole. The entry second minus 1. Okay, for experiment 3, same method. This rate over the reactant concentration. So K equals to 0.0175. Okay. So this is the first way how we calculate the rate constant. Okay, let's see question number 2. B. Use the formula T half equals to calculate the value of rate constant if the half-life is 480. Okay, so K equals to 0.693 over T half, which is 480. Wait a minute. There is an elephant here. Okay, 1.44 times 10 to the power negative 3 second minus 1. So very easy, yeah? Just remember this formula. So K equals to 0.693 over T half. Of first order ratios has a rate constant of this. This is rate constant, which is K. Calculate the value for the half-life. So now we need to get the half-life value. So 0.693 over the K. 7.196 seconds. Okay, so we are done with rate constant calculations. So look here. Okay, through this second video, I already explained about calculating the rate of reactions graphically. Yeah, by the concentration versus time. Yeah, this is for the reactant and this is for the product. All you need is just to make the triangle something. Yeah, find the tangent. Okay, find the tangent. That's how we calculate the rate of reactions graphically. Okay, and then we already learned about the rate equation. The rate equation equals to K times concentration of reactants to the power of their order. Okay, this is rate equation. We can find the rate equation through the experimental data. Okay, and we also already learned about rate constant K, but how to calculate the rate constant using the initial concentration and initial rate. We can find the K through the graph, okay, of the rate versus concentration. Yeah, we can find the value of K through graph, or we could find the value of K through the half-life value, 0.693 over T half. So we are done with this, and this. I hope you already understand. If not, you can review once again, watch this video once again. Okay, thank you everyone. We will see each other again at the third video. Okay, at the third video. The third video will cover about what? About this. Yeah, about order of regions, half-life, blah blah blah. Okay. Bye bye.